Swayam Prabha. Digital India. Educated India.
How are you? Fine? Enjoying the campus. A lot of activities going on in SAC. Probably all of you must be knowing it, right? Did you get a chance to go there, or you need a permission or something? You needed a permission. So you can watch from outside. Right? You went inside. Oh, good. Yeah, I think now we have 20 some more. Should we wait or shall we get started? We can get started, right? Yeah. So in the last lecture of mine, I think I introduced you to the electronic transitions that can happen in an organic molecule. Right? We talked about non-bonding transitions from non-bonding levels. We also talked about electronic transitions from the pi bonding levels, and then we also talked about electronic transitions happening from the sigma, filled sigma orbitals. And we talked about various transitions which could be like n to pi star, n to sigma star, or pi to pi star, and then sigma to sigma star. And we summarized at the end saying that sigma to sigma star transitions require very high energy, and that's typically in the range of 200 nanometers. If you translate it to the electron volts, you would know what is the number. And hence, observing sigma to sigma star transitions are very difficult in the ultraviolet, because it's seen in the far ultraviolet region of the electromagnetic spectrum. So it is quite challenging. But the common transitions that you can notice when you record an UV visible absorption spectrum is pi to pi star and n to pi star, right? So these are the two possible transitions that are observable when you use a spectrophotometer and record them. You can notice these two transitions. We started off with simple alkene, ethylene. We said ethylene has an absorption at around 175, right? And then we added one more double bond to ethylene. Then it becomes a butadiene. This butadiene system is conjugated. If you record the usable absorption spectrum, you would notice an absorption band 175 roughly plus 30, so you would see it around 200 nanometers. And from 200 nanometers or 220 nanometers onwards, you will be able to see it quite readily, because spectrophotometer can give you that kind of a freedom. You can monitor these transitions. So in ethylene and butadiene, the main transitions that are responsible for absorption is pi to pi star. It can also undergo sigma to sigma star, but that you will see it in the far ultraviolet region, and hence it is not noticeable. But then we came to another class of molecules. We took simple acetone, which has only the carbonyl. It has pi and non-bonding as well. So the possible transitions are pi to pi star and n to pi star. N to pi star is transitions usually occur at a very lower energy. So you will see it at a longer wavelength when compared to that of the pi to pi star. So you will see two bands. One is of less intensity and another one is of a greater intensity. N to pi star transitions typically is observed around 280 nanometers or so, with a very low molar extinction coefficient. In the case of pi to pi star, you would be able to see the band very evidently because of the very large molar extinction coefficient. Molar extinction coefficient is what? The probability of electronic transitions, right? How much this, with how much probability that these electrons could be transitioned to the higher energy level. Greater the electron density on the backbone, larger is the probability. Okay, so conjugated systems are supposed to have a very large molar extinction coefficient. With this introduction, we took to the classical example of beta carotene, right? We talked about an example of retinol. So these are some of the examples that we said. Retinol is yellow in color, beta carotene is orange in color. When we look at the absorption maximum and molar extinction coefficient, we start to see that these bands are appearing in the visible region. So if something is colored, you know that it has an absorption in the visible region. Right? So this is what we summarized. I think after that, did we say anything? No. We also talked about one particular aspect where you have a donating group present in an arene system. For example, a benzene has a donating group on one end and the acceptor group on the other end. If they are appropriately placed in a way that they can communicate between themselves, right? You can move the lone pair from the donor and take it to the acceptor to the other end, then this system could exhibit color. We said it is a push-pull system. We also called it as a donor-acceptor embedded arenes, and hence an extended conjugation is possible through these donor-acceptor systems, and hence you can see the absorption in a colored spectrum, which is the visible spectrum. And we also said many of the dyes do have this kind of a property. When you engineer such dyes, you always keep the donor, let the donor talk to the acceptor. Okay, so this communication you have to ensure in order to have a simple structure with a nice visible spectrum. And beta carotene also, you remember, right? It has 11 double bonds in conjugation. So adding on double bonds, not going to help, but you need to come up with a different design strategy, and hence donor acceptor systems are colored. Okay, with that brief introduction, now I will take you to the main topic which we were supposed to discuss in the previous lecture. So this is a photochromism, the property of a reversible color change between two different species is called photochromism. It is a reversible process in a way. So you start with species A as is shown here, right? You shine light onto this system. It immediately changes to species B. It generates a new species, which is B. Switch off the light, which means you are not giving light irradiation, but thermally it is now getting activated because just switch off the light, but room temperature is available for the system. Now this B can transform to A. Right? Don't get confused. There is a notation which also tells us HNu prime. Forward reaction has HNu. Backward reaction from B to A has HNu prime. What it means? You have to use different wavelengths for these processes to happen. So it is a light-based activation or wavelength-based activation whereby you can transform one particular species to another species. Okay. So by switching these wavelengths or switching the light, this is a red light for example, I have a blue light. So you can turn on the system to convert it to A to B using green light. I can use the red light to transform the B to A. So you can now correlate in terms of optical memory, some terms that you have heard across when you are reading, right? Optical memory devices. So it's kind of a memory device where you can use this light to switch on back and forth and switch off back and forth. Okay. So this is the actual process. In this process, what happens basically is you start from a colorless system, usually. This is a common practice. You can also start with color 1, end up in color 2. That's also possible. From color 2, you can revert to color 1. It is possible. For example, let's say we are starting off with the colorless compound A. Shine light onto this. It will undergo a light-based transformation, which will give you compound B, right? This compound B is supposed to be colored. So if you record the ultraviolet absorption spectrum, right, for this compound A, where do you think its absorption will be? Colorless compound A. That is a clue. Where will you see its absorption will be? ultraviolet region, it should have the absorption. Only in the ultraviolet region you should see the absorption. So, in the ultraviolet region of the visible absorption spectrum, you have an absorption band for compound A. Okay. Now, I switch on the light of certain wavelengths. I know where this compound is absorbing, right? Where it is absorbing in the ultraviolet region. I can take any wavelength, for example. So, from 200 to 400 nanometers, I can choose any wavelength. That range is ultraviolet range, and I know this is where my compound A is absorbing. I choose a wavelength, pick a wavelength, hit it to A, right? I hit it with this particular wavelength on A. What in this process happens is, it absorbs light, it undergoes a photochemical transformation, some structural modification happens, which is supposed to be reversible, so it is mostly electronic rearrangements. And then what happens is, if I switch off the spectrum, the moment you generate species B, upon impinging light onto it, what you will see is, you will see a new band appearing in the visible region. Right? What has happened in this process, the intensity of this has come down, and there is a growth in the absorption in the visible region. That tells you that A is getting consumed in the process, and you are seeing a new band evolution in the visible region, which is responsible for B, or this is coming from B. That is the information you get, right? Now, if you record the absorption spectrum for this species, this is absorption spectrum. Now, I have to revert it to A, then what is the wavelength you have to choose? Choose the visible region, and the species that you have generated is B, and that has an absorption in the visible region. So, only if you shine visible light, this species has a chance to absorb, it can come back to A. This is one way of looking at it, right? You can also ask me, sir, why don't I choose this region? It also absorbs in the ultraviolet region. What if I choose the ultraviolet region? You can choose. It would come back, again it would come back. So, you will not be able to completely pushing it to A. You will end up in a scenario where you will have an equilibrium of these two, because this, you shine with the ultraviolet region, this species also absorbs, will get transformed to A. This will get transformed to A. So, this equilibrium will be established. You want to completely push it to A from B, then choose the absorption which is newly evolving or newly evolved, and take this absorption and choose this as a wavelength for irradiation. Hit it with B, and you will get transformed. You will get the transformation from B to A. Okay. So, this is one of the ways by which this process, back and forth process, which is a photochemical transformation, could be observed by visible absorption spectroscopy. Not only the color, but physics in principle. We are excited about colors, conjugation, disturbance and all that. But physicists, they are mostly worried about this refractive index change. The species A probably may have a different dielectric constant when compared to species B. So, they are worried about the physical properties undergoing a change in the process. So, physics people are more interested in this too, and chemists also are interested in oxidation reduction potential, and physicists to some extent, right? Because you are transforming a structure of A to a different structure altogether, which is the cause for the absorption of the visible region, and hence their structural properties are different. Their redox properties should also be different, and because these two species have different forms in the solution, refractive index of them could also change, and you will also see the dielectric constant being different. These molecules, as I said, have application, or this property has application in our ophthalmic lenses. This I had told you in the previous lecture itself, right? Other than that, it also has fancy applications. I said, kids putting t-shirts, plain white t-shirt, when they roll in sun, they will find out that the t-shirts change. There are also interesting applications in abroad. Okay, it's not moving. Yeah. So, this is a building, okay, which is coated with photochromic paints. right? Now you will see the building is facing sun. I mean, this part of the building is facing the sun. Now whenever sunlight comes up, falls on the building, because it's coated with photochromic paints, they undergo color transformation. Okay. When the sun goes to the other side of the building, this will become its natural color, such as this, silvery white. Okay. These are some fancy applications you will notice all over the world, and some of the applications that you will come across is in the ultraviolet radiation filters in some of these glasses. Okay, we have these kind of glasses, right? So people coat it with photochromic paints, and it filters off the ultraviolet radiation that gets in, because the coating has molecules that absorb ultraviolet radiation and filters all the ultraviolet radiation that penetrates through this glass and gives you the healthy radiation. It filters off the ultraviolet radiation hence. So as a result, the building is protected. You also get a cooling effect because everything is knocked out, right? You get a healthy radiation that comes in, so it gives room is illuminated with a dull environment around. Okay, so such kind of applications even in cars, flights, and trains now, high-speed trains in abroad, all of them are getting transformed with this kind of paints. Or some electrochromism also is another aspect that people are exploring now, where with a low voltage impulse onto these paints, they would transform color. Switch off the electricity, they would come back to its natural color. Okay, so such kind of filters are being used with the help of such kind of materials. History is so long, it is not new anyway. They started from 1867. First example was on tetrazine, but this was recorded in the observation saying that there was color change, but no one knew that is a photochromic phenomenon. Okay, tetrazine compound is orange in color, as we discussed in the previous class also. Annulating benzene rings linearly would extend the conjugation, and you will see the HOMO-LUMO energy gap getting decreased. We see that more of pi electron density, you destabilize the HOMO, all that we discussed. So there is energy gap decrease. So absorption is in the visible region, and these tetrazine compounds are colored, they are orange colored. Fitze in 1867, when he placed this molecule at optimal conditions, as the time passes by, he observed a color change from orange to becoming colorless. So he was surprised. He took this colorless compound, he heated it, it once again gave him the orange color. Right? So he thought there is some color change associated. He didn't know what is going on those days, but he observed and recorded in his observation saying that this particular compound underwent a color change, which we could notice. This was the very first observation. Now you know the reason as to why this particular compound undergoes or loses its color. Do you know or not? Last class we discussed about it. I drew the structure of the dimer. Yeah, it forms this dimeric structure, butterfly type structure, right? So it's the monomeric compound under photochemical conditions gives you the dimeric compound, thereby breaking the conjugation, and hence this orange color is lost in the process. You get a colorless substance at the end, which is corresponding to that of a simple naphthalene. So naphthalene is colorless, and so we will see the absorption in the ultraviolet region. So that was the story now. Okay, but the first example, the first notice was made by Frege. Then came 1876, Termere. He was also using a potassium salt of dinitroethane. Okay, it has acidic hydrogens. You can remove the hydrogens by treatment with base. He got a potassium salt of it, and this potassium salt, upon storing, it loses its color. This was the second observation made in 76. And then there was a zinc pigment made by Phipson in 1881. He also noticed a color change with this zinc pigment, but the origin of it was not clear at that point of time. And in 1899, Marquardt was the first person. He saw a similar observation of color change, but he thought he could connect it to a natural phenomena which is a phototropy, right? Plants move towards the sun and then harvest light, right? So in a similar fashion, he saw there is a change that is being observed with the help of light. So he could connect it to phototropy phenomena, and hence he called it as phototropism. This was his word this was Marquardt's word. Then this area slowly picked up. Hirschberg and Fischer did extensive studies on such kind of color changing materials. He came up with a term which is photochromism. He was the first person to coin this name to such color changing molecules by light. Okay. And the 60s, 70s, 80s, 90s, now in 2000s, I think there are a large number of examples on photochromism. The literature is growing. What people are working on, simply put, is that mainly to control the kinetics, how rapid this color change could be. How slow can you make this color change is the research that is actively going on, because some of the industries are looking for fast response, quick responsive materials, right, and shape changing materials. So all of that, these processes back and forth, right, reversible processes, how can it be controlled? So that understanding is evolving, it is still evolving, and some of the molecules have successfully made the market. They have gone into industries and large scale applications. As I showed some of them now, you will see they are finding applications everywhere. What are the type of systems available? When you look at this structure, all of them are organic molecules. The first example, could you identify this unit? What is that unit? Pyrrole. Pyrrole, right? Pyrrole fused to benzene. As you can see, there is a benzene, there is a pyrrole. So this compound's name is indole actually. Okay? And thiophene fused to benzene, you call it as benzo-thiophene. So this is a benzo pyrrole. You call it as indole. Indole is a common name, right? And this unit you may be familiar with. What is that unit? Can you identify? It's an anhydride unit that is there somewhere, right? And if you don't have these two exocyclic double bonds, you can call them as, it is a this anhydride must have been derived from the dicarboxylic acid. Have you come across any dicarboxylic acids? Succinic acid, malonic acid, right? So this should be from succinic acid. It's a succinic anhydride unit. What is more important here is not to know the name of the molecule, but you just look at this pi structure here, right? Here is an alkene unit. You have an alkene unit here. You also have an olefin unit here. These three are like a triene system, right? You have 6 pi electrons involved in this triene system, but this triene is acyclic because they are not connected in any way. It's a cyclic, it's a triene system. Now when you shine it with light, what happens is there is some electronic rearrangement, as I said, has happened. What has basically happened is you will see that there is a pi bond here, there is a pi bond here, there is a pi bond here. So there are 3 pi bonds, your attention should be on. At the end, what you are seeing is you have created a sigma bond between these two, right? And how many number of pi electrons are there here? 1 and 2. 6 pi electrons have now become 4 pi electrons. Then what happens to the other pi? That has become a sigma bond. Electron count is same. You started with 6 pi electrons, 6 electrons. Ultimately, you are generating 4 pi electrons and you have constructed a new sigma bond involving 2 electrons. So, totally electron count remains same. It is just an electronic rearrangement that has happened, reorientation of the pi electrons. Now, you have created this sigma bond. Okay, this is species B, which is supposed to be colored. This is species A, which is supposed to be colorless, right? And why this is colored, why this is not colored? When you have such a system, you look at this region particularly, highly sterically crowded with all these methyls everywhere, right? So they wouldn't be achieving planarity. This system, if you look at just the 6-pi system, they wouldn't be achieving planarity. There's no way, and hence they would deviate themselves from planarity, and as a result, you disturb the conjugation. When can you have effective conjugation? What is the condition? When the orbitals are all parallel to each other, and the angle of them should be, they are parallel, it's 0, right? When can you break this conjugation? Let's say one of the p orbitals you are twisting it, right? And you move it to about 90 degrees, let us say. At that point of time, there is a conjugation broken. So if you are coming up with a system which cannot achieve planarity by any way, then you will certainly see a disturbance in conjugation. Right? I am giving it very qualitatively, just to make you understand. Right? 90 degrees means need not be necessarily 90 degrees. It could be somewhere 85, somewhere 80. Right? Still, you are disturbing or you are decreasing the pi electron movements across the backbone. Then obviously you are disturbing the conjugation, and hence you will see absorption in the ultraviolet region. Now in this case, once you have formed the sigma bond, right? Now if you look at that particular cycle, this particular cycle, just flip it. When you look at like this, you will see that the methyl, one of the methyls are going up, another methyl is going down the plane, and this methyl also one goes below the plane, and the indole unit flips up. What you see is this particular unit remains in planarity, and you can have extended pi conjugation from this nitrogen, jumps all the way, goes here, and then reaches this carbon. There is an extended conjugation established in the cyclic form of this molecule, right, when compared to the acyclic form that it was in. Okay, so this switch, transformation of 3 pi bonds to 1 sigma bond plus 2 pi bond, is technically, in textbook you will find it as pericyclic reactions. There is a set of reactions, those are called pericyclic reactions. This is one class in pericyclic reaction. This is an electrocyclic reaction. It's an example for an electrocyclic reaction. Electrocyclic reaction means you can form a cycle via electronic rearrangements from an acyclic system. You can open the cyclic system and form an acyclic system. Both these forward and the backward processes are denoted as electrocyclic reactions. This is completely different from your regular reactions that you study in your textbooks. Because you would have studied nucleophilic substitution reactions, SN1, right? Elimination reactions, U1CB, all that. Even aromatic electrophilic substitution reactions, nucleophilic substitution reactions, all that. But all of them are ionic reactions. They generate intermediates. They also generate byproducts in the reactions. At least water could be a byproduct, many of the reactions, right? So, byproduct is there. In these kind of reactions, you operate them with either heat or by light. These are the conditions you use. You don't add any reagents contaminating the reaction. No byproducts are generated. You will not involve any intermediates in the process. No cations, carbocations, no anions, no carbon ions involved in the process. That means what? It bypasses this intermediate. What you have is only the transition states. Start from reactants, passes through the transition states, and then results the product. There is no intermediate that is generated in the process. So what it should involve, from a cyclic form to an acyclic form, and to a acyclic form to a cyclic form, both the processes must involve a cyclic transition state, which is a 6-membered cyclic transition state. Right? So what is the reagent here? Only electrons and light. Very, very beautiful reaction. One such example is electrocyclic reaction. Another